Section 3.3 is measure of position, and this is the last section that's going to be covered on our test on next Wednesday. The objectives here are to compute and interpret z-scores, compute the quartiles of a data set, compute percentiles of a data set, look at the 5-number summary, understand the effects of outliers, and then also to construct a box plot and visualize the 5-number summary and outliers. You may not know right now what most of these words mean, and that's okay. We're going to get into it as we go along. Objective 1 is to compute and interpret z-scores. I guess it would help if we first understood what a z-score was. A z-score is the number of standard deviations a data value is above or below average. If a data value is above average, it will be positive. If the data value is below average, it will be negative. And that comes from how we calculate the z-score. The formula for calculating a z-score is we take our data value minus the mean or the average value, and then divide that by the standard deviation for the distribution. In a minute we'll see this formula written out with symbols, but I think this might be something that will prove helpful to you to put on your formula sheet so you can see what it is in terms of words. We can use z-scores to answer questions such as this. It says, who is taller? A man 73 inches tall or a woman 68 inches tall? The obvious answer is that the man is taller, just at face value. However, men are taller than women on average. Suppose the question is asked then, who is taller relative to their gender? A man who is 73 inches tall or a woman who is 68 inches tall? Do you see how that question's different? The first question just asks for raw observation. Clearly the man's going to be taller than the woman. The next question asks who's taller among their gender. Is a 6'1" man going to be taller among men than a 5'8" woman among women? In order to answer this second question, we have to calculate z-scores. And like I said, the z-score is just a number that represents how many standard deviations a particular data value is, either above or below average. This is the formula that I was talking about. Z is equal to our data value minus the mean divided by the standard deviation. Remember, this symbol right here, mu, is the population mean. The symbol sigma right here, the lowercase sigma, is the population standard deviation. That's why I gave you this formula. And I said that if your data value is above average, meaning it's bigger than average, you're going to have a positive z-score. The standard deviation will always be a positive number. Depending on your data value could be positive or negative, and same thing for the mean. Your z-score will be positive only if the data value is bigger than the mean, because you get a positive number if you take away something small from something large. Your z-score will be negative if your data value is below average, meaning less than average, because then we take a smaller number and subtract a bigger number from it, and that's how we get the negative z-scores. So if a z-score is positive, it's above average, and if the z-score is negative, it's below average. Your data value is below average. Let's look at this example now where we talked about the heights, the relative heights of men and women. A National Center for Health Statistics study states that the mean height for adult men in the U.S. is 69.4 with a standard deviation of 3.1 inches. The mean height for adult women is 63.8 with a standard deviation of 2.8 inches. Then we're asked the question, who is taller relative to their gender, a 73-inch tall man or a 68-inch tall woman? If we calculate the z-score for the man's height, we're going to plug in his height that we were given in place of x. That's the 73 inches right here. Then we use the average for all men's heights, 69.4, and divide by the standard deviation. When we do that, that gives us a z-score of 1.16. For the women's heights, we plug in the 68 inches for x, then the women's average height for mu, and then the standard deviation of 2.8. That gives us a z-score of 1.5. Which would be taller relative to their gender? The woman, because she's more above average. Do y'all remember us talking about the normal distribution? It looks something like this. And we said what number goes in the middle? The mean. And then we go out one standard deviation, mean plus sigma, and then mean minus sigma. What percentage of data fell within this range? 68% of all data fell within this range. And then if we go out another standard deviation, there's mean plus 2 sigma and mean minus 2 sigma. What percentage of data fell within that range? 95% fell within that range. And if we go out 3 standard deviations, we're looking at almost all of our data. If I change these numbers down here to the z-scores, what number is going to go right here in the middle? If it is average, remember how we calculate the z-score is our data value minus the mean. Right here, if I plugged in the mean for my data value, I would have mean minus mean is 0, and 0 divided by whatever the standard deviation would be, 0. And I told you a z-score represents the number of standard deviations something is above or below average. So if I move to the right one standard deviation, what would be the z-score that I associate right here? It's one standard deviation above the mean. Do you see how this is the standard deviation that I've added to the mean? If my mean is 0, the standard deviation would be 1. In red, I would have the z-score associated with that number. What would be the z-score right here, the mean plus 2 standard deviations? It would be 2 because I'm now 2 standard deviations above average. The question was, how did I figure out this was 0? If we start with the z-score formula, it would be the data value minus the mean divided by the standard deviation. Right here in the middle, we have the mean. So if I want to know what the z-score is associated with that, I would just drop the mean here in this formula in place of x. That would give me the mean minus the mean divided by the standard deviation. Well, mu minus mu is 0, and 0 divided by anything is 0. That's how I came up with this, or this z-score being 0. I also told you that a z-score is just the number of standard deviations above or below average something is. At this point right here, mu minus sigma, what would be my z-score? A -1. And then what would be my z-score right here? -2. What you see in blue would apply to any normal distribution. What you see in red is something that we're going to call later on a standard normal distribution because we've standardized our distribution. The percentages here for the data that's in between within one standard deviation of the mean, those remain constant for any normal distribution. The 68% of your data will be within one standard deviation. If we're looking at z-scores, that would be numbers between -1 and 1. If we're looking at z-scores and we move out to 2 standard deviations, that would be numbers between z-scores between -2 and 2. You've seen what I have in blue. What did that come from? Do you remember what that's called? Starts with a E. The empirical rule, which leads us to z-scores and the empirical rule. Since the z-score is the number of standard deviations from the mean, we can easily interpret the z-score for the bell-shaped populations, also known as normal distributions. When a population has a histogram that's approximately bell-shaped, then approximately 68% of our data will lie within one standard deviation of the mean. Remember, the z-score represents the number of standard deviations above or below average. If you're right at average, the z-score is going to be equal to 0. 68% of our data would be between -1 and 1. 95% of our data would have a z-score between -2 and 2. And then almost all of the data would have a z-score between -3 and 3. That almost all is actually 99.7%. Your book doesn't make a big deal out of that, but other books that I've seen do, and I don't know where you're going from this course, so I just want to make that point. Objective 2 is to compute the quartiles of a data set. Quartiles, another word for quartiles, is quarters of your data. Let's say I have a uniform distribution here, and I wanted to divide that distribution into quarters. Well, if I draw a line down the middle, I've just halved it, and that number in the middle would be our median. If I cut that first half in half again, now I've got quarters of my data. And then I cut the last half in half, that gives me quarters of the data on the last half. This number right here would be what we call Q1, our first quartile. It's a capital Q with a subscript of 1. Our minimum data value would be the number right here that draws this first line. Then we have Q1, Q2 is the median or the middle value, Q3 is the third quartile, and then our maximum value would give us this other side over here. All 5 of these numbers right here are called a 5-number summary, and I'm getting a little ahead of myself because we're going to go over that again in just a little bit. Quartiles divide our data into equal parts where the parts are 25% each. The first quartile separates the lowest 25% of the data from the highest 75%. The second quartile, denoted Q2, separates the lowest 50% from the highest 50%. It's the same as the median. On your graphing calculator, you won't see it referred to as Q1, you'll see it referred to as median. The third quartile then separates the bottom 75% of the distribution from the top 25%. Are there any questions about what a quartile does or what it is? These are the steps that you can go through for computing quartiles by hand. Because in this course I'm teaching using the TI graphing calculator, I'm not going to worry about doing this step. We're not going to worry about calculating quartiles by hand. We're going to look at how to calculate them on the graphing calculator. On the graphing calculator, we're going to be using something that we're familiar with, and that's the one variable stats. Do y'all remember how we got to this screen? Stat, go over to calc, and then just press enter. But before you're ready to go to this screen, what do you have to do first? Put your list of data into the calculator, and that's where we're going to start. So on your TI-84 Plus graphing calculator, I want you to type this data into your calculator. I don't care which list you use. The following table presents the annual rainfall in inches in Los Angeles during the month of February from 1969 to 2013. Compute the quartiles for the data. And we're going to do this on our graphing calculator. After we have our data in our list, what do? Second quit. You go back to the home screen. How do we go to the home screen? Second mode. Then to get our one variable statistical analysis, we hit stat, go over to calc, and then hit enter. And this is what my home screen looks like right now. I don't have a frequency list though. We only use the frequency list if we're going to be doing something with a frequency table. I did put my data in list 1, so for my list I'm fine, but for my frequency list that needs to be blank. So make sure that your frequency list has nothing in it, and then we hit calculate. And if we scroll all the way down to the bottom, remember those arrows there mean that there's more information below. If we scroll all the way down to the bottom, we'll see this screen. This should be the list that your data is in. And then this should be blank unless you're doing work with a frequency distribution. And then when you hit calculate, the first thing you're going to see is X bar, but if you scroll all the way down to the bottom, you'll see what's called your 5-number summary, and that's going to give us that Q1 is equal to 0.81, the median or Q2 is equal to 3.12, the third quartile is 5.24. N is your sample size. That means that there's 45 pieces of data here. So I have 3 rows of 15 is what this boils down to, right? If I wanted to calculate the median by hand, how would I do that? I need to find the middle data value, right? I've got 45 listed in order from smallest to largest. How would I find the middle number? If I have 45 pieces of data, it would be 45 divided by 2, and that gives me 22.5. Because this is not a whole number, that means I have an odd number of pieces of data. I would go up to the 23rd data value, and that would be my median. So there's 15, 16, 17, 18, 19, 20, 21, 22, 23. This would be my median. Does everybody agree? That's what we got here, isn't it? 3.12. Now, if this is my median, that means there's 22 numbers to the left, 22 numbers to the right of the median. Do y'all remember me saying that it's the middle value? And for our quartiles, if we look back at this, how I got this median was, or how I got my quarters was, I said, okay, let's find the median, and then I cut the top half in half again and cut the bottom half in half to get my quarters. Going down to my data values, if I take these first 22 numbers and treat them as if they're another data set and I find the median of those 22 numbers, how many numbers would I have to go over? Where would the middle be? There'd be 11, and then I'd be right smack dab in the middle, right? That's 15, 14, 13, 12, 11. At this line, I have 11 data values to the left and 11 data values between that and the median. So then I would take the average of those two middle numbers. And so to get the first quartile, that's what I do. I take the average of these two numbers that are the median of the top 11. Are you with me? 0.7 plus 0.92 is, and then I divide that in half and I get, do you see why I had to average those two numbers to get Q1 when all I did was I looked at the middle for the median? Now look at the numbers to the right of the median and I've got 22 numbers again. I count over 11 and find out where Q3 is going to be. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So right here I separate out 11 numbers between the median and this number, and then 11 numbers to the right of that line, and I take the average of these two numbers to get Q3. Q3 would be equal to 4.94 plus 5.54 divided by 2. And what do we get when we do that on our calculator? 5.24. So you see how the calculator is giving us the right answer without going through all that rigmarole of counting. Let the calculator do the heavy lifting for you. And for quartiles, we're perfectly content letting the calculator do the heavy lifting. Let's look at visualizing what the quartiles look like. Your 25% of your data may or may not be evenly spaced. Following is a dot plot of the Los Angeles rainfall data with quartiles indicated. The quartiles divide the data set into 4 parts, with approximately 25% of the data in each part. There's our rainfall data listed out. Notice most of our 25% is bunched up. The distance from the minimum value to our first quartile was very small. But if we go out to our fourth quarter, the distance from the third quartile to the largest value is spread out. When something like this happens, we say that that distribution would be skewed right because the long tail goes off to the right. Alright, the next objective then is objective 3, computing percentiles of a data set. If quartiles divide our data into quarters, the percentiles are going to divide our data into percents, or 100 equal pieces. Quartiles describe the shape of a distribution by dividing it into fourths. Sometimes it's useful to divide a data set into a greater number of pieces to get more detailed description of the distribution. Percentiles divide a data set into hundredths. So for a number p between 1 and 99, the pth percentile separates the bottom p percent from the highest 1 minus p percent. For example, let's say that you took a standardized test, say the ACT or the SAT. They give you a raw score when they send you their results. They also tell you what percentile your test score fell in. So if they told you that your test was in the 83rd percentile, what that means is out of all of the people that took the test, your test score would have been up here. There's your test score. And you scored higher than 83% of the people that took the test. What percentage of people scored higher than you? 17%. So if you're looking for the 83rd percentile, that P there, just replace that with 83, and 100% minus 83% would be 17%. That's how you read that. I wasn't sure if that was clear. We're going to go over these procedures that we follow for finding percentiles, and then we're going to go through an example. And I think even if this is kind of fuzzy and seems unreal or difficult to follow, once we go through an example, I think it'll make more sense. The following procedure computes the pth percentile of a data set. Your first step will be to arrange your data in order from smallest to largest. Remember, in order to find medians, we had to arrange our data in order from smallest to largest. Same thing with percentiles. You need to have your data sorted from smallest to largest. Once you do that, we let n be the number of values in the data set. N is our sample size. For the pth percentile, we compute L. L here is called a locator. That locator just tells us what position in the list of data our percentile will be. It's just the physical address, more or less, of the particular data value that you're interested in finding a percentile of. When you use this formula, and that's all it is it's a formula, if L is a whole number, then the percentile that you're looking for will be the number that's in that position of the whole number plus the next position. You just average those two. It's the average of the numbers that is in the L and the L plus 1 position. If L is not a whole number, we round up to the next whole number, and then that's going to be the location of the data value that corresponds to the given percentile. Once again, we're going to be using the data that's already in our calculator. Thank God, right? We don't have to type it in again. We want to compute now the 60th percentile of the data set. Let me write down the formula for you. The locator is going to be the percentile divided by 100 times n. For this particular problem, we're asked to find the 60th percentile. So P will be what? 60 divided by 100 times, and then we said we had how many pieces of data here? 45. Now we go to our calculator and we type in 60 divided by 100, or 0.6, times 45, and that gives us 27. 27 is not the 60th percentile. 27 isn't even a number in the list. It's the location of the number, the data value, that represents the 60th percentile. Now, this is a whole number. So I need to take the number that's in the 27th position and the 28th position, and I average those two numbers together. My answer here will be the average of the 27th and 28th numbers in our list of sorted data. There's 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, and 28. I look at these two numbers right here. The percentile score will then be 3.57 plus 3.71 divided by 2. The 60th percentile will be equal to, and what do we get for a numerical answer? 3.64. So 3.64 would be in the 60th percentile. Let's try another one. This time, and this isn't part of the problem, I'm just making this up, I want you to find the amount of rainfall that corresponds to the 32nd percentile. To do this, we find our locator. The locator is going to be P, which in this problem is 32, divided by 100 times n, and n is 45. Doing this on our calculator, that's going to give us 32 divided by 100 times 45, and we get 14.4. 14.4 is not a whole number, so we round this up to 15. The data in the 15th position is P sub 32. The 15th piece of data happens to be this last number right here. This is equal to P sub 32. The only time you have to do the average is if your locator comes out to be a whole number. If it's anything else, you round up to the next whole number and go with the number in that position. So for this problem, P sub 32 is equal to 1.48. Do you see the difference? Let's say it was 14.01. If our locator came out to be 14.01, I would round up to 15, and then the number in the 15th position would be the Only if your locator comes out to be a whole number do you have to do the average of two numbers. I want to make that point clear. That's something that I've said that you probably need to write down, or it's in step 3, but I don't think that it was clear when we read it. If our locator is a whole number, the pth percentile is the average of the number that we got for L and the next number. That's what I said right here. Since my locator was a whole number, I take the average of that number that I got and the next number, and then I average those two numbers together to get the percentile score. If L is not a whole number, we round up to the next higher whole number. Even if it would have been 14.01, we round up to 15. This is not your traditional rounding, it's just going up to the next whole number. That's why for the next one, the one that I made up, when we got 14.04, we round that up to 15, and then the number that was in the 15th position was going to be the data value for the 32nd percentile. Alright, we've learned to go one direction. Now we're going to learn to go the other direction. Now if I give you a data value, can you tell me what percentile that data value is? This is a little bit different. So sometimes we're given a value from a data set and wish to compute the percentile corresponding to that data value. Following is the procedure for doing this. Step 1 is the same as it was before. Arrange your data in order from smallest to largest. Step 2, we let x be the data value whose percentile is to be computed, and then you use the following formula. The 100 is just to change this number to a percent. We take the number of values that are less than x, add a half, and then divide by the total number of numbers that are in our data set. Once again, our rainfall data. We don't have to type in anything new. We're happy. We're told the following table presents the annual rainfall in Los Angeles during February from 1969 to 2013. In 1989, the rainfall was 1.9 inches. What percentile does this correspond to? Now we're looking for the percentile. What I need to do is I go to my 1.9, which is right here, and I want to count how many data values are less than this. So the formula is my percentile is equal to 100 times, and I'm not going to write this down again, it's up here. How many data values are less than 190? Well, there's 15, so 17, and then we have to add a half to it, so that's where we get the 17.5 from, divided by how many data values do we have in total? 45. We have 3 rows of 15. If we put this into our calculator, what do we get? We get 38.9. What that means is in 1989, that 1.9 inches of rain is what we would consider being in the 39th percentile. I would probably, if I would have got 38.4 here, I probably would have said the 34th or 38th percentile. This number is traditional rounding. Only on the locator do you go up all the time. There were 17 pieces of data that were less than this particular number, and then I add a half to it, so that's where the 17.5 came from. Adding a half is part of the formula. And then we divide by the total number of values that are in our data set. That would be our sample size. Is it making sense? It needs to make sense because you're going to have to know how to do this on your homework. Objective 4 is to compute the 5-number summary for a data set. I've already told you what the 5-number summary is. It's just the bottom 5 numbers that you see on your calculator whenever you do the one variable statistical analysis. So for our rain data right here that's already in our calculator, let's find our 5-number summary. We already have the data in our calculator. How do I find the 5-number summary? Stat, calc, enter. Make sure you only have list 1 here and nothing for the frequency. Go down to calculate. And then this arrow right here means that we have more information below. So we scroll all the way down, and there is our 5-number summary. Our minimum value is the smallest data value that's in our set. That's 0. Q1 is the first quartile, and that's 0.81. Q2 is the median, and that's 3.12. Q3 is our third quartile, and that's 5.24. And then your maximum value is 13.68. It's pretty straightforward. We use this 5-number summary, though, to identify outliers and make a box plot. Objective 5 is understanding the effects of outliers. Do you remember when I drew this box right here? We said that our quartiles divide the data set into quarters. This middle set of quarters, this middle 50%, is something that we call the IQR, or the interquartile range. The interquartile range is just the middle 50%, and we use the interquartile range to help us identify outliers. An outlier is a value that is considerably larger or considerably smaller than most of the values in a data set. Some outliers result from errors. For example, a misplaced decimal point may cause a number to be much larger or much smaller than other values in a data set. Some outliers are correct values and simply reflect the fact that the population contains some extreme values. The temperatures in a downtown location is measured for 8 consecutive days during the summer. The readings in Fahrenheit are as follows. Do you see a number in this list of data that looks like it might be an outlier? It looks like 8.45 degrees might be an outlier because we're looking at days in the summer and all these numbers are between 80 and 90 degrees. Basically, that 8-degree day would be below freezing, and that might be an error. Odds are whoever wrote that number down just put the decimal in the wrong place, and maybe that data value should have been 84.5. That seems reasonable. If you weren't the one that did the data entry on that, though, you need to talk to the person that did and ask them to go back and look at their data and make sure that that is in fact what happened. If it was, then you can make the correction in your data set and carry on. If it was not a typo, let's say that we had a fluke cold front come through and drop the temperature down to 8 degrees. You need to keep that data value then, and it's just something that would occur naturally. It's a natural phenomenon. The outlier 8.45 is certainly an error, likely the result from misplaced decimal point, and it should be corrected if possible. If, however, we had a fluke cold front come in, that would be a sampling error. You've got to deal with it. I mentioned the interquartile range before using this picture up here. I wanted the picture there because it just fit on the paper nicer. But the interquartile range is just that distance for the spread of that middle 50% of your data. How we find the interquartile range is we take the larger number minus the smaller number on the bounds. We just find the range of the middle 50%. So that would be Q3 minus Q1. And that's given in the formula right here for interquartile range. The way we calculate the interquartile range is we look at Q3 minus Q1. This is going to be a positive value because we're taking a smaller number away from a larger number. If a data value is more than 1.5 IQR above Q3 or below Q1, we consider it an outlier. Your first step for detecting an outlier then would be to find your quartiles, then find the interquartile range, then multiply your interquartile range by 1.5 and subtract that product from Q1 or add that product to Q3. Anything beyond those values would be considered an outlier. In this example, we're told that the following table presents the number of students absent in a middle school in northwestern Montana for each school day in January. Identify any outliers. The first thing we've got to do to find our outliers is identify what the IQR is. So the IQR here would be equal to Q3 minus Q1. What is Q3? 59 minus 45. And what's 59 minus 45? It's 14, isn't it? Once you know what your IQR is, you want to find 1.5 times your IQR. On your calculator, you would just type in 1.5 times 14. And that would be 21, I believe. If somebody will double check that, I'd appreciate it. Now, to see if your number is an outlier on the low end, we would do Q1 minus 21. And this is just the formula from your notes. Now we're going to find this by plugging in numbers. Q1 is 45 minus 1.5 IQR is 21. And what's 45 minus 21? How many? Our minimum data value is 41. So we don't have any outliers on the low end. To get an outlier on the high end, we would look at Q3 plus 1.5 IQR. Q3 we said was 59 plus 1.5 IQR is 21, and 59 plus 21 is 80. Do we have a data value greater than 80? Look at your max. We have 100, so we have at least one outlier. That means that this number right here is an outlier because it's above 80. It's bigger than 80. Is it the only data value bigger than 80? Yes, it is. So we only have one outlier in this set of data. So for this particular problem, your data value is an outlier if it's less than 24 or greater than 80. That means that 100 is an outlier. Objective 6, the last objective this evening, is to construct a box plot and visualize the 5-number summary and outliers. A box plot is a graph that presents the 5-number summary along with some additional information about a data set. There's several different kinds of box plots, and your calculator will do 2 of the kinds. This one, wherever you mark your outliers with asterisks, is called a modified box plot. On a modified box plot, we use an asterisk for any data value that's more than 1.5 IQR away from the box. So these data values would be more than 1.5 IQR above Q3. On a box plot, these would be considered outliers. No matter if you're using a regular box plot or a modified box plot, how you make the box is going to be the same. The first number on this box is Q1. The median will be that line in the middle of the box, and Q3 will be the line that forms the upper bound for that box there that's in the middle of these whiskers. You may have heard these called box and whisker plots. The minimum value goes down here. Typically our maximum value would go up here unless it's a modified box plot, in which case this would be the max number that's not an outlier. And then if you have any outliers, you would include them. Let's look at making a box plot on our calculators now. So we need to put this data into our calculator. Actually we don't. I've got the output here. We'll do a box plot for the data that we have in our calculator. Don't change the data in your calculator. The following table presents the number of students absent in a middle school in northwestern Montana for each school day in January. We want to construct a box plot. First thing you need is a scale here, some way to show the relationship between your numbers. We're going to use the 5-number summary, so our minimum value here is 41. 41 is about right here. That's going to be my minimum value. Then Q1 is at 45. 45 is about right there. The median's at 51. That's about right here, just eyeballing it. The Q3 is at 59. That's almost 60. And then the max value is 100, and that's going to be out here. We take these middle 3 lines and make a box, and then we draw a line from end to end for the whiskers. And this would be a regular box plot. If you want to do a modified box plot, you look for the next biggest value other than 100, and what would that be? It'd be what? 77? If we did a modified box plot, these numbers would be the same, but our maximum value would be 77, which is going to be about right here. And then we just put an asterisk for our 100 to show that it's an outlier, and this would be our modified box plot. The reason you may want to look at a modified box plot is because you can tell something about the shape of the distribution if you didn't have that outlier there. This looks almost normal, and we'll talk about the shape of a distribution looking at box plots in just a second. This was modified, and this is just a regular box plot. Let's do a box plot on our calculators. You've got your data in your calculator. If we want to graph our data, we go up here. All of the buttons for graphing are going to be up here. If you hit y equals and you have something in your calculator right now, clear it out. I was graphing these functions in Cal 2 earlier today, so let's clear these out just to make sure that we don't get any kind of overlap with graphs. If you want to do a graph for statistics, you got to do your stat plot. So I need to hit second y equals to hit my stat plot. Then I hit enter to turn on my stat plot. To turn your plot on, you just hit on, move your cursor to on, and hit enter. Right now I have a histogram highlighted. If I want a modified box plot, I would do this 1, 2, 3, 4th graph. I just want to do a regular box plot, so I'm going to do the one that's the fifth graph. Move your cursor over to the box plot that you want and hit enter to select it, and then it asks for what list your data is in. Leave the frequency alone. As long as that's lit up, your plot is turned on, you should be able to hit zoom 9 in order to see the best picture possible. So we hit zoom 9, and there's my box plot. How would I change that to a modified box plot? Just go back, hit second y equals, and I change my graph to the modified box plot, which is the fourth one over there, and then we hit zoom 9. Zoom is the number in the button in the middle on the top, and that shows that I have 2 outliers in that list of data. You want to do it again. Alright, so you've got your data in your calculator. Let me start from the home screen. You hit second y equals to go into your stats plots. And these steps are written out for you in your notes. You put your data into the list, then you go to the home screen. If they leave out that step right there. Select the plot that you want. Select the graph that you want. Make sure you turn it on. To turn your plot on, you just move your cursor over to on and then hit enter. To select your graph, you scroll over to it. If I want just the regular box plot, I'll hit enter on that. Then it asks for the data list, or the list for where your data values are located that you want to graph the box plot for. Then you just hit zoom 9 once that's set, and it adjusts the window for you. If you forget the steps on how to do graphing on your calculator, they're in the notes. This is the last thing that we need to talk about tonight, and I will be asking questions similar to this on your test. Box plots can be used to determine the skewness of a data set. This histogram appears to be skewed how? Skewed to the right. Remember, the tail tells the tail. The tail is going off to the right. This box plot represents this histogram. Do you see how this bottom 25% has the longer, it takes a greater distance to cover that bottom 25%? And I don't know if I made this clear before. This first leg of the box plot represents 25% of your data. That's pretty close together. Your second quartile here also represents 25% of the data, and then the right side of the box is 25% of your data. So this last tail, this last 25% has got a much longer range of values that it's spread over. That means that your distribution would be skewed right. For this histogram, our distribution is what? Because the tail is going off to the left, we would call this skewed left. And look at the box plot. On the box plot, this 25%, the bottom 25%, has a much longer tail than the width of either that second quarter of data, or the third quarter of data, or the fourth quarter of data. This would be an example of a distribution that's skewed left. And then on this distribution, we called that what? Symmetric and bell shape is normal. Notice the box is in the middle for a normal distribution. The tails are about the same width or the same length on the whiskers, and the box is in the middle and the median's in the middle. That's one way that you can tell what the distribution is just by looking at a box plot. And this wraps up section 3.3, chapter 3, and all of the material that's going to be on our first test.